Namaskar children. Continuing with the refraction of light, in today's session we are going to understand how light ray refracts when it passes through a glass slab and when it passes through lenses. Firstly, we'll understand how does refraction of light takes place in a glass slab. First, we are going to view the activity for the same and then we'll draw the ray diagram. So you can see how a ray of light incident on the glass slab shifts from its original path and emerges out of the glass slab. This is due to refraction of light. There is a shift in the emergent ray and the actual path of the incident ray. To draw the ray diagram, we'll mark the 2 points for incident ray, one where it strikes the glass slab and one point would be somewhere on its path. So we have marked the 2 points to draw the incident ray. Now you can see the light has bent from its original path and it has emerged out from a direction which is slightly shifted from the original direction. So we'll mark the emergent ray as well. We'll mark a point on the path of the emergent ray and we'll also mark the point where the ray of light is emerging out of the glass slab. So these 2 points will help us to draw the emergent ray. So now we use the 2 points to draw the incident ray, one where the light is striking the glass slab and one point on its path, that is the incident ray, and also we draw the emergent ray by joining the 2 points, one where it emerges out of the glass slab and one point that we marked on its path. So tracing the path of light through a glass slab, suppose this is an incident ray which strikes the glass slab at this point where we have dropped a normal. So light is traveling from a rarer to a denser medium, from air into the glass slab. If this is angle of incidence, angle between the incident ray and the normal, light will bend towards the normal since it is entering a denser medium and the speed of the light decreases. This here is the angle of refraction, angle between the refracted ray and the normal. When light strikes the second interface, that is when light is now going from glass to air, at this point on the interface, we draw another normal. And since light is going from a denser to a rarer medium, this time light will bend away from the normal as its speed will increase. And this angle here is the angle of emergence, angle between the normal and the emergent ray. Now looking at the ray diagram, we can clearly see that the light ray has shifted from its actual path. This dotted line here is representing the incident ray which would have travelled in this path if the glass slab was not here. Since there was a glass slab in between the path of light, it has deviated from its original path due to refraction of light, and this is now the actual path followed by light. The perpendicular distance between the actual path of light and the initial path which the incident ray was following is known as lateral shift or lateral displacement. It is represented by small d. In this experiment, we will also observe that the angle of incidence and the angle of emergence are equal. This is something that we will observe experimentally also when we perform the experiment in the lab. Also, this lateral shift here depends on the angle of incidence. More is the angle of incidence, more is the shift. It also depends on the thickness of the glass slab. Thicker is the glass slab, more will be the lateral shift. It is directly proportional to the refractive index of the glass slab. More is the refractive index of the glass slab, more will be the bending and hence the shift will be greater. And it is inversely proportional to wavelength of the incident light. This here is the symbol for wavelength. Inversely proportional to the wavelength or the color of the incident light. More is the wavelength of the incident light, smaller would be the shift. So that would mean if I do this experiment with the help of a red laser and a blue laser, I would observe that a red laser will be shifting less from its actual path, since the wavelength of red is more as compared to a blue laser light, which is going to shift more as compared to the red laser, since the wavelength of blue is less. So these are the four factors on which this lateral shift or lateral displacement through a glass slab depends. So this is a commonly asked question in the exam, where you have to trace the path of light through a glass slab and label the angle of incidence, angle of refraction, angle of emergence and lateral shift. So the next topic that we are going to discuss is refraction through lenses. Now what do we mean by a lens? Lens is a transparent material bounded by two surfaces, in which one of them is spherical and other is either spherical or plane. So this means we can have different type of lenses. As you can see here, these are the different types of lenses, but we are going to study in detail only two of them. These will be biconvex lens and biconcave lens, or simply convex and concave lens. We will be discussing these two lenses in detail. You are already familiar with some of the properties of these two types of lenses from your previous classes. We'll just recapitulate those. So a convex lens is the one which is thinner at the edges and is thicker in the center. So that is how we draw the symbol of a convex lens. It is thinner at the edges and thicker at the center. This lens is also known as a converging lens, as it converges the light that falls on it. What do we mean by that, and why does this lens behave in this way? We'll just discuss. So let us try to understand, why does a convex lens behave like a converging lens? So suppose this is a convex lens here, and this is a light ray which is incident on the lens like this. Now light is going from a rarer medium air to a denser medium glass. We know whenever light goes from a rarer to a denser medium, it bends towards the normal. So we'll draw the normal on this surface. This is the surface where light is going to strike first. So we drop a normal to this surface. It's a curved surface, it's a spherical surface. So the normal would be somewhere towards the center of this sphere, like this. So this light ray, which is entering from air to glass, is going to slow down and it will bend towards the normal. So bending towards the normal would be something like this. It has bent towards the normal, otherwise it would have gone straight if the lens was not here. So due to this lens here, a glass medium here, it has gone towards the normal. Now when the light strikes the second surface, again now light is at the interface. It is going to go from a denser medium to a rarer medium, and this time the light is going to go away from the normal. So I drop a normal on this second surface, which is also a curved surface, a refracting surface. This time the normal to this surface would be in this direction. And this normal to this surface which we have drawn, this light ray is going to go away from this normal, because it is going from a denser to a rarer medium. It is speeding up and it will go away from this normal. It's going away from this normal. So did you observe the path of light? It was entering in this direction. It has bent from its original path, and this is what has happened. Similarly, if we would have considered another parallel ray to this first ray, following the same rules, this ray would have bent in the opposite direction, like this. On the other hand, a concave lens is thicker at the edges and thinner near the center. So this is the symbol for concave lens. It is thicker at the edges and thinner at the center. It is also known as a diverging lens. Suppose this is a concave lens and this is a light ray which is incident on the concave lens. Again, light is going from air, a rarer medium, to a denser medium, and when we try to trace the path of light through this type of lens, again we drop a normal at this surface, the first refracting surface, which is curved in this direction. So how do I drop a normal on this surface? It would be in this direction. If this is the spherical surface, this would be the direction of the normal. So this light ray which is coming from a rarer to a denser medium is going to bend towards the normal, because it is going from a rarer to denser medium, it is slowing down. So it will bend towards the normal. So this is how the light ray would bend inside the lens. And again, when the light ray is about to move out of the glass lens, where it is going from a denser to a rarer medium, it will speed up and it will go away from the normal. When we draw the normal in this case, this is the spherical surface. The normal at this point would be in this direction, perpendicular to this surface. And this light ray, which is going from a denser to a rarer medium, will move away from this normal and it will go in this direction. Moving away from this normal, it will go in this direction. So you can see the path followed by the light here. This was the incident ray, this is the refracted ray, and this is how it emerges out. So it's a diverging lens, whereas a convex lens was a converging lens. So these property of lenses will help us to understand the topic further. So this is the practical demonstration of our discussion. You can see the set of 3 laser lights, and when a convex lens is placed in the path, you can see that the lens converges the light passing through it, and the light rays meet at a point on the other side of the lens. So this shows that convex lens here is behaving like a converging lens, whereas if we used a concave lens in the path of the laser, we can clearly see that the light rays are getting diverged from the lens. It's a diverging lens. We'll now discuss some of the important terms related to lenses, just as you have already done for mirrors also. The first term is optical center. It is the central point of the lens, labeled as optical center. Next is principal axis. Now these spherical lenses can be assumed to be a part of these spherical surfaces. If I complete the sphere with the help of these curves, I can mark the centers of these spheres. Similarly, a concave lens can be assumed to be a part of these spherical surfaces, and these are the centers of these spherical surfaces. Now the line joining the centers of these two spherical surfaces and the optical center of the lens is known as principal axis. Of course, it is an imaginary line. because only this much portion is the lens. This dotted sphere is imaginary. We have just completed this curved surface of the lens, and we have completed this side of the curved surface as well. We marked their centers, and this imaginary line passing through the centers of the two spheres and the optical center is the principal axis. Similarly, in case of a concave lens, these are the two imaginary spheres and this is the optical center. When we join the centers of these imaginary spheres and the optical center, we get an imaginary line which is the principal axis. So, principal axis is an imaginary line which is passing through the optical center and the center of curvatures of the spherical surfaces. Next is principal focus. This is one of the most important terms that we are going to define for lenses, and we'll do it separately for both the lenses. So first let us define the principal focus of a convex lens. So I have drawn a convex lens here, and I have also drawn the imaginary line, that is the principal axis. If parallel light rays fall on a convex lens, it is observed experimentally also, and we have shown you theoretically also by drawing the diagrams that how a light ray which is parallel to the principal axis, how does it bend and it ultimately converges. So it is observed that when parallel light rays fall on a convex lens, after refraction they meet at a point on the principal axis, and this point on the principal axis is labeled as principal focus. It is represented by capital F. I again repeat, how do we define principal focus of a convex lens is, it is that point on the principal axis where parallel light rays after refraction meet. So, principal focus for a concave lens now. I have drawn a concave lens here, drawn a principal axis also, and marked the optical center. Now suppose parallel light rays are incident on a concave lens. We observe that after refraction, these light rays will get diverged. And if I produce back these diverged light rays, they appear to meet at a point on the principal axis, and this point is labeled as the focus of the concave lens. So how do we define this point? It is that point on the principal axis where parallel light rays after refraction appear to diverge from. What does that mean? To an observer this side, these light rays will appear to come from a point behind the lens somewhere here. It would appear to the observer that these light rays are coming from here at this point. So, principal focus for a concave lens is that point on the principal axis from where parallel light rays after refraction appear to diverge from. The last important term that we are going to discuss for lenses is the focal length of the lens. It is the distance between the optical center and the principal focus of the lens. So, in this diagram, you can clearly see the distance between the optical center and the principal focus. This distance is known as the focal length of the lens. Similarly, for a concave lens, this is the distance between the optical center and the principal focus. So, this is the focal length of the concave lens.